say that again. Welcome everyone to Recitation 12, Graph Neural Networks. This is a continuation in our ordinary series we've been talking about so far in deep learning. The professor asked me to talk about graph neural networks because I have some research experience with them. So I'm going to be presenting that to you guys today, not the research, but talking about them. So I guess the basic intuition behind a graph neural network that I wanted to give you guys is, and another thing that would be kind of interesting since there's so few of us, if you guys want to turn on your microphones, we could have sort of like a discussion in person that would kind of keep us going.
Yeah, that's fine. I might stay muted until I have things to say, if that's cool.
Sure, that's fine. Perfect. Okay, so I guess the basic intuition behind a graph neural network is that it is an artificial neural network that operates upon graphs, which sounds kind of intuitive from the name. As you know, I'm guessing you guys know what a graph is. Is that correct?
Yep.
Yep.
Cool. Quentin, I'll ask, what's a graph?
Basically like a connection or a set of like nodes with connections between them, and it can be directed or undirected, but yeah.
Exactly. Yeah, exactly correct. Yes. So that's what a graph does. A graph neural network operates on data that can be represented as graphs. So in a sense, they are kind of like a generalization of all the stuff we've learned about before, right? So when we talked about MLPs, they had, say, a vector input, or when we talked about CNNs, they had an image input, or when we talked about RNNs, they had, like some kind of sequential input like text, for instance. The idea is you could represent all of those as a graph, and you could, in theory, put that through a graph neural network and have it learn useful information on the graph instead of the raw data itself. So in a way, graph neural networks are, you can kind of think them as like an attempt to generalize everything we've learned about the more conventional neural network types. Does that make sense?
Yeah, I think so.
Cool. Yes, let's see here. Checking my, yeah. So that's the basic intuition behind them, I would say. Sorry, I'm trying to gather my thoughts. Yeah, let's see. So thinking back to our what we've learned so far in the class with the more conventional neural network types and the data we've been using, how could we maybe like say represent something as a graph?
So like we've been doing a lot of sort of sequence stuff with language based on this description here. So like would the entity be the kind of token that we're talking about, and then the relationship to each other?
It could, absolutely.
Be the kind of, just like we've talked about, like context between, word 1 and word 7 or, stuff like that.
Yep, certainly.
Yeah.
Absolutely, certainly. It could also be, it doesn't have to be tokens. You could do probably whole words or even whole sentences or maybe whole paragraphs in theory, right? Granted, they'd be more computationally expensive, but the idea is theoretically, since you can represent all of this sorts of data as a graph neural network could handle it. So
yeah, is like the attention in transformers also like a graph representation, because we have self attentions and multi-layer attentions going from one token to other tokens as well, right?
Yep.
And within it.
Yes, exactly. You could think of it that way. Again, with transformers, since they are more of like the, they're using like more standard data, just raw data input. It's typically not thought of that way, but you absolutely could. I think there is actually something called like graph attention networks or graph transformer networks that actually implement that exact idea. So yeah, good question. Perfect. Anything else? before we move on? Okay. Yeah, so that's the basic core idea behind GNNs. And so with that, I think we can scooch to theory, section 2. So in order to know about GNNs, you kind of need to know a little bit about graphs. It sounds like you guys already kind of do with graph theory. You know about the definition of a graph. You have a set of vertices and a set of edges, and the graph is the tuple between them, right? And I'm guessing you guys probably know that graphs can be directed or undirected. They can be weighted or unweighted, and there are plenty of other types of graphs as well.
Yep.
Okay, good. So graph neural networks can indeed be applied to all sorts of different types of graphs. Normally in the wild, you'll see them normally applied to, say, directed graphs. Most paradigms kind of default to the graph being directed. That's just usually the assumption. It's also simpler to calculate, so that's typically what they're centered around. Yeah. And so weighted versus unweighted graphs. Let me think. When I put that there, it's maybe a little bit of a misnomer. Saying a graph is weighted, when it says where it says each edge is a weighted graph is a numerical value or a weight. A more abstracted way of thinking about that is what we call an edge embedding, which is where each edge in a graph has some attribute information tied to it that the graph wants to learn. That could be like a single scalar value, or it could be, like a matrix, or it could be some other object. It doesn't have to necessarily be just a single scalar value, but for a simple example, normally that's the case, but it does get more abstract than that. Yeah. So for graph representations, 2.1.2. There's different ways of representing graphs when it comes to GNNs. I'm sure you guys are familiar with matrix representation, and how when you have say a sparse object, it kind of gets redundant storing all that information. So a graph has a corresponding thing called an adjacency matrix. It tells you the connections between nodes. That again gets kind of redundant if you don't need all that information. So sometimes in practice, we'll use what's called a feature matrix. Yes, right. And that reduces the amount of data you have to store to represent your graph. Because it just matches, it doesn't store, it's more like a list, right? Or like a dictionary. If you were to do it in Python, it doesn't store unnecessary information. It'll just tell you what the actual important edge values are between nodes, right? So you can reduce the total number, the total number of necessary information there. And then several graph properties. I just listed a few here. Again, I'm sure you guys are familiar, like degrees of vertices, paths and cycles. I'm sure you've heard of other properties as well. We probably don't need to get too into that at the moment. Okay. So for graph neural networks, one thing that's very interesting about them is, when we've looked at like MLPs and CNNs and RNNs, we've had to kind of revise our notion of training these things, right? And what that means in terms. When we first started learning about MLPs, it was relatively straightforward. But when we moved on to CNNs and RNNs, thinking about what does back propagation mean in multiple dimensions? What does back propagation mean through time? All of these more generalized and abstract notions, right? So let's talk a little bit about that. What did you guys learn from, say, going from an MLP to a CNN? What did you guys learn about the differences in the training paradigm? and backpropagation.
I mean, so obviously there's like differences in complexity of how to implement it, but I guess to me, like the underlying thing obviously stayed the same, which is like you can draw what kind of turned out to be a graph in itself of like the causal, well, the relationship between inputs and outputs, and then what, you know, the edge in this case would have been the kind of like multiplicative factor that updated stuff. And then so obviously that picture gets way more complex as you go to things like CNNs, but the underlying idea is quite the same, is that you have an input, there's some kind of causation that happens that gets to the output, and you work backwards through that.
Exactly.
And CNN is like a time delay in your network of MLP.
Yes, exactly. That's what I was going to add on to, is like if you can recall, when we went from like MLPs to CNNs, for instance, right? The jump was, it seemed fairly logical, but we had to add these extra tools for CNN for doing learning, right? So we needed to learn about, convolution, upsampling, downsampling, padding, et cetera, right?
Yep.
So we had to learn these tools that in a sense kind of generalized what we had previously learned with our MLP model. Does that make sense?
Yep.
Good. And so it's kind of a similar process here with GNNs as well. One thing you kind of might have gotten at this point, I don't know if any of you guys were here when I did my first recitation, which was actually on MLPs this semester. I tried to tell you guys, instead of thinking about layers in a neural network as, just like matrix operations followed by activation functions, it's easier if you can think of them as like a staging operation, or like a filter that transforms the data, right? And you put one on top of the other, and through each one of these stages, each one of these layers, it transforms your data slowly but surely, right?
Yeah.
Graph neural networks are no different in that sense. So in other words, you have your graph, which is some input data, and you apply a graph layer upon it. It's called a convolution. That's just part of the old literature. We call it a convolution on the graph. It's more generalized than that, but it's just out of respect for CNNs. A lot of the research of graph neural networks came out of convolutional neural networks, so they kept the name. But it's the same idea. You have some graph that has some initial data. You send it through some kind of layers in your graph neural network that constitute your graph neural network, and it modifies the data associated with your graph, which could be at the edge level. It could be the information associated with the edges, the edge embeddings. It can be with information associated with the nodes, the node embeddings, or it can be something to do with the whole graph itself, the graph embedding. And so each one of those are respectively an edge level task, a node level task, or a graph level task. Or you can do any combination thereof simultaneously. And so with that, as far as the actual training paradigm, the paper that was very seminal with this was by Gilmer and his ilk. They discovered this interesting paradigm for training graph neural networks that pretty much all of them kind of fall into. I wish I had some visuals to show it, but I'll do my best to explain it verbally. So if you look at the equation under update functions, that one right there. So what they did is they broke the message passing operation down into three functions, or three operations. The first one is called message UV, and that passes some message from node U to node V. And that this message function could be whatever you want. It could be defined by it could be a hard-coded function, or it could also be some other differentiable model, right? So it could be an MLP, it could be itself a CNN, it could be an RNN, whatever you like. Followed by that, so what that function does is it's taking some information from node U, it is modifying it in some way, and it is passing that along to node V. After that, we have the aggregate function, which aggregates all incoming messages from to node U, right? So if node U has neighbors, in this case, we're saying it's a single neighbor V, but it's abstract, right? You can have multiple neighbors. The aggregate function tells node U how to take all of these information it's receiving from its neighbors and how to aggregate it accordingly. Normally, this is a fairly simple function, like say averaging, or it can be max, it can be the min of all of the incoming data, but it's just some way of reducing the incoming data. That's why it's called aggregate. And then after that, there's the update function, right? And you'll notice it's a function of the aggregated values and h of v. H of v is the hidden state of the node. So in other words, the node's new that, or we typically call it the hidden state. Normally, it's an encoding of the node's embedded values, or it could just be the node's values themselves. But normally, there's some function acting upon the node's embeddings, which are being passed to this update function along with the aggregated information. And then that becomes the new hidden state of the node V. Sorry if that was kind of wordy. Did that make sense? If I'm not making sense, please tell me.
I think so. I mean, just to try and restate it, it's like, so each hidden state of a given node will be a function, right, of its like some initial hidden state, and then like the connections between it and its neighbors.
Correct.
But,
yep. But before that, the whole process is node U has some message which it sends to its neighbors V. V can be a single node or it can be multiple nodes. And then from that, it receives messages from all of its neighbors, which it aggregates in some way. And then from that, it uses its own internal state and those aggregated messages to update its internal state.
Okay, cool.
Yeah. Maybe that's a simpler. Maybe I should have just said that to begin with. Anyway.
No, the initial is helpful too.
Okay, good. And so each one of these functions here, message, aggregate, and update, they can be simple functions in some way that are hard-coded, or they can themselves be differentiable models like MLPs, CNNs, RNNs, etc. So that's kind of what's something that's fairly interesting. And then they become learnable, right? Did that part make sense?
Yeah, I think so.
Okay, good. Let's see. Yeah, the next piece is just more of that. It's telling you a little bit more about the aggregate function, which again can be, it's normally like mean pooling or max pooling or min pooling or something, but it's some way of just reducing the data. That's not really important for right now. Learning node representations, that I think, Dennis, you can probably get that with your code representation, your code demo.
Yeah.
Okay, so tasks performed by.
Actually, could I ask one question? So like
when
we talked about it was CNNs where there was sort of the underlying motivation had the idea of like a simple cell and a complex cell, right? Where the what was it? The simple was sort of like the kind of convolution itself, and then the complex was the idea of like max pooling, say, right? And like kind of filtering stuff out. Is it fair to think of this a little bit as like the message function, whether it's simple or like an MLP, is kind of like the simple, and then the aggregate is kind of like the complex cell, or is it just not really helpful to try and draw a connection there?
I wouldn't simple and can you define what you mean by simple and complex? I think I have
So
an
just
idea.
like in the context of the CNNs, where like the simple would be the idea of just like the convolution itself, and then the complex being the kind of filtering of like a max pooling, say.
I see. Yeah, in that case, that would basically kind of be it, except this would be just mathematically, this is a more generalized idea. So this would actually encapsulate what we've already seen with CNNs.
Gotcha. Okay.
Yep. I think we're 2.3 tasks performed by GNNs. Sorry, were there any other questions before we move on? Okay, guess we're almost done with the theory part before we get to the fun stuff. I'll try to finish up here. As I mentioned earlier, there are three primary tasks you can perform with graph neural networks. One of them is a node level task. That's where you modify the information associated with each node. This normally comes in like, your classification tasks or regression tasks like you've seen with all your other prior models. So if you have like nodes in a network, maybe you have and each node belongs to one of two possible classes. You can apply, say, a node classification task and have your neural network learn from the context of the graph what class each node belongs to over time. You can do the same thing with regression. If there's like some information associated with each node, you can have the graph neural network learn what that information is supposed to be, but it's on a continuum, right? Instead of a discrete classification. That's, I guess I call that feature learning here, but same thing. Link prediction is the same thing as a regressive task, but applied to the links. So if you have embedded data with whatever your links are, in the case of, now that I think about it, can anyone think of a very simple example that we've already seen that would be a link prediction task? The beginning of the semester? Anybody? What are some ideas? What? And I'm going to pick on you because you've been so helpful.
Oh yeah, no worries. I mean, I'm like my mind is going towards MLPs, but could you give one more, like just repeat the description of link prediction? I'm reading through, but like okay, my reading is we're trying to decide should an edge even exist between two nodes? Is that correct?
Oh, I see. Oh, sorry. This is the wrong thing. I put link prediction. I meant to also include link regression as well. My bad.
Okay.
My bad. Good eye.
Oh yeah, no worries.
Yes. Sorry. With regards to link regression, can you think of a simple example we've already seen earlier in the semester that would be directly correlated with that, classified with that?
I mean, just kind of trying to figure out what the weights are in an LP.
Exactly right. Where each edge would be just a scalar value, right? Your weight.
Mm-hmm.
But in a graph neural network, we could abstract that further and we could have those embeddings be anything. Sure, they could be a single scalar value, or they could be a vector of values or matrix or tensor or what have you. But yes, it's exactly the same idea.
Okay, cool.
Does that make sense, guys?
Yep.
Good. Additionally, same thing with link prediction. Like we mentioned, should it belong there? Should it not? Et cetera, et cetera. Finally, graph level tasks. It's about learning There's graph classification and graph generation. For example, graph classification that's often used for things like chemistry, to find like chiralities of molecules or different variations of molecule types. You can have a graph neural network learn, if you give it this graph corresponding to a certain molecule, is it of the same family as a chemical corresponding to a slightly different graph? It's kind of a rough way of saying it, but I think you get what I mean. Graph generation, also you can perform similar tasks for having them generate graphs as well. Yeah. Cool. So that's, I think, my piece. Are there any questions about that? Sorry, it was kind of long. Okay, guys. With that, I think we'll turn it over to Dennis.
All right. So now we shall be moving on to the practical side of graph neural networks. And here we're going to be using the PyTorch geometry library. So yeah, it's a powerful library for deep learning on graphical structured data. So we shall have a series of hands-on exercises. So like we've just looked at, we have two basic tasks that we shall be covering here. That is a node classification and graph classification. In node classification, like we've seen, you're implementing a GNN model to classify nodes in a graph. So for this particular instance, we shall have we shall apply graphical neural networks to the task of node classification, in that you have a few nodes within the graph that are labeled and would like to label the rest of the nodes in the graph based on a few examples that are labeled. So it's they refer to it as translective learning. So to demonstrate, we shall use the Cora dataset, which is a citation network where nodes represent documents, and each node is described by 1,433 dimensional bag of words feature vector. So two documents here in this dataset, two documents are considered connected if there exists a citation link between them. The task is to infer the category of each document, and we have 7 categories in total. So if, for example, one citation appears in both documents, so we shall consider those documents linked. So here in this cell, we provide some description. So the dataset was first introduced by Young as one of the dataset or planetoid benchmark suite. And we again can make use of our PyTorch geometry for an easy access to this dataset via the torch geometry dataset planetoid. So you can see here we import it here, and we also import normalize features. So in this line, we go ahead to create our dataset using planetoid. Then we pass on the root and the name of the particular dataset that we're interested in, which in this case is Cora. And we apply a transform like we usually do for images in CNN. We normalize our features, and now we can look at the properties of this dataset. So so here we'll go ahead and print the dataset, the length and number of features and classes. Here I'll go ahead to interpret what each of them means. So here we have 2,708. Those are the number of nodes in the graph, as we had earlier explained. You know what nodes means. Then we have edge index, which is 2 by 10,556. What this means is that we have sort of two tuples which show the connections between the nodes in the graph. So I don't think we have an example of that, but it shows if for instance, node 0 is connected to node 1, there will be a 1 between those two. And if the node 2 is connected to node 3, there will be a 1 like that. So it shows some form of connection. But since this is an undirected graph, we have to show both both sides of the connection. So if node 1 is connected to node 2, then we shall have node 2 being connected to node 1. That's why we have these two here. Then y, which is the target, that's the target classification. So since here we are classifying individual nodes, each of the nodes has a label to it. That's what the y here represents. Then we have train mask, validation, and test mask. So here, what these are used for is they show which of the nodes are going to be used as part of the training dataset, validation dataset, and test dataset. So this masks out some parts of the nodes for us to classify. So here we break it down. Number of nodes is 2,708, as we can see from X in our data here. Then number of edges is 10,556. But in this case, we have two because we have to show both directions since it's an undirected graph. We are showing the average node degree. So this shows how many edges on average, each node has within the graph. Then we have the number of training nodes, which is 140, meaning out of the 2,708 nodes existing in the graph, we're only using 144 for training. Then the training node label rate, that shows what percentage of the overall data set we're going to use for training our network. And the has isolated nodes false. So this one shows whether there is any node that's disconnected from any of the other nodes within the graph. Then having self loops, I think Kasi touched on it earlier. So in graphs, we can have it's such the way the graph is designed, it's connected to neighboring nodes, but sometimes we don't want to lose the information that's contained within the particular node that we are dealing with. So we usually insert a self loop that is from the node back to itself, in addition to the connections of that node to its neighboring nodes. Then we have this other property which is undirected, which is true, given that we have connections between. If node 1 is connected to node 2, then we shall consider that node 2 is connected to node 1. And all these properties can be accessed. For example, the number of nodes. Once you've created your data set, if I could go back here. Once you've created your data set, we can get the first graph object within this data set by indexing it using 0. So we obtain the first graph within the data set. The number of nodes can be accessed using this data.number of nodes, the number of edges as well. Then the average node degree, we obtain that by dividing the number of edges by the number of nodes. Then the train data, we can do that by applying the sum to the train mask. Then the node label rate as well, we divide the number of data points that are in the training data set over the total number of nodes that exist within the graph. Then for these other properties, we can check as isolated nodes, we can check using as isolated nodes property, and has self loops as well as is undirected. So now
so what does accessing first graph object mean? Is it like we have multiple graphs in the data set?
Yeah, so we're
Yes, that's true.
Yeah, we're accessing only the first graph.
And all the graphs are independent, or are the graphs also linked to each other?
No, all the graphs are independent. So it's sort of considering a batch of graphs.
Okay.
Just as you would have a batch of data, right? In an ordinary task.
Yeah.
Yep.
Yeah. So I get the idea, but in a normal bunch of data, it's like different samples belong to the same class, something, right? So here, do we have different graphs belong to this with the same node structure as such, graph structure as such, or?
Yeah, I think that would be the kind of way of thinking about it. So you have within each graph, we have nodes that belong to particular classes.
Okay.
But these two graphs are not connected. The graphs within the dataset.
And what exactly does number of training nodes mean?
So the way you'd usually break up your dataset. So given a dataset, for example, we we usually hand out our datasets in this course by when they're already split into validation, train, and test. So this is the same kind of thing you'd think of, whereby here already by the from the library itself, they provide it when it's already broken down. So they just apply a mask to some of the nodes, and those nodes will have labels attached to them.
Right. But we have like, can you scroll down a bit?
Okay.
But we have like 2,700 nodes and we have only 140 training nodes.
Yeah, that's that's the way it was designed for this particular dataset.
Okay. Okay.
Yeah. Yeah. So here we can see that the Cora network holds 2,708 nodes, 10,556 edges, resulting in an average node degree of 3.9. I think now the node degree should be clear. For training this dataset, we are given ground truth categories of 140 nodes. So only 140 nodes are labeled for this data set. So this results in a node label rate of 5%, which we looked at. Then the graph holds additional attributes. That's the validation mask and test mask, which denotes which nodes should be used for validation and testing. So furthermore, we make use of the data transforms via transform is equal to normalized features. Transforms can be used to modify your input data before inputting them into the neural network. So for normalization, as we would do in our other tasks in deep learning. So now we're going to make an attempt to perform this task using an MLP and compare its performance with that with when we use a graph convolution network. So in theory, so yeah, as explained in this cell, in theory, we should be able to infer the category of a document solely based on its content. That is, it's a bag of words, feature representation, without taking any relational information into account. So we can verify that by constructing a simple MLP. So for example, in this cell, we go ahead to create an MLP which is composed of linear layers together with the ReLU activation function. We also apply dropout as we do normally in our neural networks, in our MLPs. So we create our network. Yeah. Is there any question?
No, I was just agreeing with you. Sorry.
Yeah. So here we create our neural net, we create our MLP and we print out the model. As you can see, we get its summary. So here the number of features in the first, we use the dataset number of features for the first linear layer, then pass it to, we create a hidden channels and finally pass it to the number of classes. The output is the number of classes. So here we describe the network that we created above, and we are going to train it using course entropy loss, given that it's a classification task, and we shall use the Adam optimizer. In addition, we shall create a test function which like checks whether our predictions are right or not. So yeah, we'll go ahead to.
Yeah. Can we go over again like why we have the 1,433 dimensions as input feature?
So okay, let's go back here. So here,
How do we
node,
get exactly that?
yeah, so each node in the graph contains a feature vector which describes that particular node.
Oh, okay. Okay.
Yeah, so the 1,433 is a vector that contains the description of a node.
Okay.
So it's feature vector, it's representation.
Got it.
Yeah.
So each node is passed to the MLP layer.
Yeah.
Okay.
So here we shall go ahead and define our train function like we usually do. Model.train, then zero apply optimizer.zero grad to clear the gradients, perform our forward pass, then calculate the loss, then calculate the gradients, and then take a gradient step to update the weights. and return our loss. Then for the test as well, we shall do a forward pass, get the edge marks, which gives us the predicted class. Then check for how many, compare the predictions with the ground truth to determine the accuracy, and return, we shall be returning our accuracy. We are going to train this network for 201 epochs. So we call this for loop. We use this for loop to train this network. So this is the training. I don't think we need to see this. I'd already run it. So the loss goes down to 0.3810 after these 200 epochs. So after training the model, we can run the test to check for accuracy. So when we run the test, we find that it only has 59% accuracy. So we can explain that. So as you can see, our MLP performs badly with only 59% test accuracy. But why does the MLP perform poorly? The reason for that is that this node suffers from heavy overfitting due to only having access to a small number of training nodes, and therefore generalizes poorly to unseen node representation. So like we had seen earlier, out of the number of nodes in the network, we only had 5% as part of our training data set. So we shall have overfitting to this small number of nodes. So it also fails to incorporate an important bias into the model, whereby cited papers are very likely related to the category of a document. That is exactly where graphical neural networks come into play and can help to boost the performance of our model. So next we shall be training a graph neural network. And so
I have a question. So
Yeah.
when we pass the input embeddings, right? I mean, if you go to the definition of our MLP layer,
Okay.
so does the embedding also consist of the information such as the node connection, as in the edge weights and all, or like what is this embedding exactly represent? How does an embedding exactly represent the node?
So here we are not trying to use the connection between the graphs.
Okay.
Here we are only trying to use the feature vector, that is the bag of words of each paper. That's given.
Okay.
Yeah.
Okay. So this MLP doesn't consider the edges between nodes.
Yeah, it doesn't consider that
Okay.
the connections between these.
Okay, got it.
Um,
And it's probably a dumb question, but what exactly are we classifying that the node is?
so we have 7 categories of documents within these
Okay.
data set as we had explained.
Okay. Okay.
So yeah, I think I could just go back here.
Okay, got it.
Hold on, let me see.
Yeah, it's over. Yeah. Okay. Right.
Yeah, so yeah, to demonstrate, we use the core data, which is a citation network where nodes represent documents.
Right.
Each node is described by 1433 dimensional bag of word feature vector. So
Right.
two documents are connected if there exists a citation link between them. The task is to infer the category of each document based on so for the MLP, we are going to base on this 1433 bag of word feature. But when we go to the graph neural network, we're going to use the connections between the nodes to determine the classification.
Got it. Thank you.
So here we shall be training our graphical neural network, and in this particular scenario, we shall be using the graphical convolution network, which is the GCN-conv module. So you can look it up. We have provided a link. You can read through its documentation, see what kind of input it expects and what kind of output it produces, so that it makes it easier for you to code. So the
GCN, sorry, wanted to interject. GCN conv is one type of layer, as you would see like in a convolutional neural network. GCN conv is a layer, and you use that to build your graph neural network in the same way you would with an ordinary neural network. Just wanted to specify that in case there was confusion.
Yeah, thank you. Yeah, so to recap the GCN layer, so I think Kelsey covered this clearly. Like we had, so you have to aggregate information from your neighboring nodes using either you can take the mean, the mean sum, minimum or maximum to in order to aggregate the information. Usually, we also want to add the information of the node itself within this. But for further information, I think you can read up on this link in addition to what Kelsey had explained earlier in terms of the aggregate function and the update function that we looked at.
So regarding real quick question regarding the Gilmer paradigm, can anyone identify the three stages here? Looking at the equation. Go ahead and take a stab. You don't have to worry, just, try to reason it out. So we had a message function, a reduce function or an aggregate function, and an update function, correct? Thinking about that nested paradigm, what does it look like each one of these is doing?
So it seems like maybe within the sum is the message, the sum is the aggregation, and then the update is the multiplication by the weights.
Yep, exactly right. You got it. And so the GCN layer performs that whole thing for us in one fell swoop. If we wanted a different schema, we would apply a different layer for, different tasks and whatnot. But yes, that's exactly correct. Go ahead, Dennis.
Yeah. So thank you for that. So then where here they describe the weights as a number of output features and by number of input features like we have usually in our weights in MLPs. So in terms of implementation, we have to import this module, the GCN conf module, and then the definition is pretty similar to what we had for the MLP. We have our hidden channels, which is like the hidden layer for this network. Usually set a seed so that it's repeatable. Then so we have conv1, which is GCN, takes in the number of features, then pass it to the hidden layer, which is like the hidden channels, then from the hidden channels to the number of classes that we have. So in terms of the forward, we pass in X and the edge index. If we went back, I think somewhere, let me see, catch that. When we're looking at so edge index is supposed to show the connections between the various edges. I think it's covered within. So you can see the edge index here. So this is 2 by 10,556, which shows the connection, the links or the connections between all the edges in the graph. That's what the edge index does. Then the X shows the number. It's the number of nodes in the graph by the feature vector, the dimension of the feature vector, which is 1433. So that's the information that we are passing on to our GCN module. Is that clear? Do you have any questions about that? Okay. If not, so here we have X, which we use a convolution, X and edge index, then we pass it through a ReLU, we apply dropout, pass it through the second conv layer and return X. So here we create our network and print it out. You can see it's 1433, which is the feature dimension by 16, then 16 to 7, since we have 7 classes. And we can easily visualize this. So we create our GCN with 16 hidden neurons. Then we convert the model to evaluation mode. then pass this is like a forward pass of our data and visualize this. So we can see there, I think it may not be easy to realize, but there are 7 classes of documents, which is illustrated in this diagram. It may not be very clear, but yeah, we shall see
How
after training the network. Yeah.
Yeah. How does edge index look like data or edge index?
Um, then so it's not currently running, but then edge index, it's sort of the representation that we talked about, that Kelsey talked about earlier, which shows which nodes are connected to each other. It shows
So
the connection.
is it like is it like a matrix representation, or is just a set of indices that the node might be connected to or something like that?
So in terms of representation here within this library, it's not a matrix representation. So we have 2 tuples. So it's 2 tuples combined. So in one tuple we have all the edges, but it's showing the connections between each of the nodes. So each of the nodes is a data point. Then if two nodes are connected, then it places a 1 to show that those 2 nodes are connected.
Yeah, I'm not able to understand how the con works in x comma edge index
So the
forward thing.
so the
Which
edge
line? Sorry.
In the 12th line of the cell, the forward con 1 of x comma edge index.
Uh-huh. Let's see.
I think if I'm to explain again, if we move back to the data set itself, we yeah. So here we go. So the information contained within X is this 2708, which is the total number of nodes that we have. Then the 1433 is the feature vector for each node. Then the edge index shows us which edges are connected. So in terms of representation, earlier we had looked at the adjacency matrix, which is used to represent a graph. So we can think of the edge index as a kind of representation for our adjacency matrix.
Gotcha. Yeah.
Does that
That
make
makes
it
sense.
clear?
Yeah.
So another way just to expound upon what Dennis said, edge index, the shape of edge index is 2 by 10,556. So can you reasonably ascertain why it is that shape, Keaton?
So it's like we have 10,556 edges. So
Yes. Yep.
and it would be the
And
source and the destination of every edge.
yep, exactly. That's
Yep.
exactly right.
Yeah. No, it makes sense.
Yep.
Okay, thank you. So yeah, we build the network as we do usually. We have our 2 conv layers, and then we return X. From there we can visualize. Visualize this is prior to training the model. These are the kind of outputs that we expect. Then now, so we certainly can do better by training our model. The training and testing procedure is once again the same, but this time we make use of the node features X and the graph connectivity edge index as input to our GCN model. So here we shall define our optimize and our loss function, and the training loop remains unchanged, as well as the test, and we run it for about 101 epochs while printing out the loss. So you can see that here the loss goes down to 0.599, and when we run uh, the test the test function, we find that our test accuracy is 81.5 compared to the 59% accuracy that we got from the MLP, which shows you a significant improvement in terms of accuracy. Yeah, so and then here we go ahead to show the final classification of of all the nodes that we had earlier. So this shows a representation of the classification after training our network. So are there any questions before we move on to graph classification? Okay.
Can anyone summarize what we just did, just to make sure we're all on the same page? Just in a couple words.
Oh, okay. So yeah, so I think
Sorry, I was asking the students.
oh, okay.
Sorry, Dennis.
It's okay.
Guys, can anyone tell me what we just did between our two accuracy values? Is there confusion? People are bored. People are tired. People just want to be done, probably.
I mean, so for the straight MLP, we were really just taking into account the features of each document. But then for this one, we took into account both the features of the document as well as their relationships to each other.
Yep. Correct. Yeah, exactly right.
And that is done with the convolution of those two informations.
Exactly right.
And the relationship between nodes.
That's correct. Yep. So as opposed to with just the straight MLP, we were able to leverage the information contained in the graph to improve our training accuracy, right?
Right. Makes sense.
Yeah. So that's the advantage we're seeing. Go ahead, Dennis.
All right. So now we shall move on to the graph classification task. So here in this tutorial, we shall have a closer look at how to apply graphical neural networks to the task of graph classification. So graph classification refers to the problem of classifying entire graphs in contrast to nodes. So given a data set of graphs based on some structural graph properties, we want to embed each entire graphs and then see in such a way that they are linearly separable given the task at hand. So we see this illustration whereby we have these graphs in blue and the graphs in green. We want to embed them such that they are linearly separable. So the common task for graph classification is molecular property prediction, in which molecules are represented as graphs, and the task may be to infer whether a molecule inhibits HIV virus replication or not. So we're going to be using the TU Dortmund University dataset, which can be obtained from this link. And here we shall again import the dataset here and create our dataset using this function, the TU dataset, passing the root and the name of the dataset we're interested in. Then we shall print some of the properties of the dataset. We have the length of the dataset, which will provide us the number of graphs, then the number of features for each node, like we had looked at earlier for the other task. Then we have number of classes. So here we have only 2 classes. Note that in this case, we are not classifying the individual nodes of the graph, but the entire graph. So we shall be classifying whether the entire graph belongs to one class or the other. Then from there, we can look at the edge index. So edge index shows the connectivity within the graph. So here we can see that we have only 38. We have 38 connections, and X is 17. So here, remember what X represents. 17 is the number of nodes in each graph, and then the 7 represents the feature vector for each node within the graph. Yeah. So then, yeah, some of those properties we had looked at already. So by inspecting the first graph object of the dataset, we can see that it comes with 17 nodes with 7-dimensional feature vectors. and 38 edges, leading to average node degree of 2.24. It also comes with exactly one graph label y is equal to 1. So here you can see y is equal to 1 as opposed to the earlier dataset where we had a classification for each of the nodes within the graph. So in addition to previous datasets, provides additional 4-dimensional edge features. However, for the sake of simplicity, we may not make use of those. So PyTorch geometry provides some useful utilities for working with graph datasets, e.g., we can shuffle the dataset and use the first 150 graphs as training while using the remaining ones for testing. So I think in the first dataset, they had already done this job for us. They had split it into the train, validation, and test, but here we shall have to do it manually now on. So here the number of training graphs, we'll split it such that the number of training graphs is 150, and we use 38 graphs for to test our method. And here this cell goes ahead to explain mini batching of graphs. So it says, as opposed to the ordinary method, we used to batch our data sets in like other tasks. Here it's we use a different method which is more efficient in terms of storage. I think we can read through this later. Yeah, so but the main point is that instead of connecting them up in batches like we usually do, they connect up the graphs diagonally. Yeah. So then here we can import our data loader and pass in the batch size that we're interested in, then make shuffle to true. That is for the train loader, and whereas for the test, we don't want to shuffle our data. Then we can print out the batches within the train loader by looping through our train loader. So we get.
Sorry, I had a quick question I wanted to pose to the class again. If you could scroll up for a moment, Dennis, to your equation right there, the figure. I think there was a question about it a little earlier, and I wanted to make sure I got it right before I answered. Do the graph types that we input to our GNN, do they have to be homogeneous in terms of their topology? What do you guys think?
Sorry, what do you mean by topology?
Do they have to have the same number of nodes, the same number of edges, and the same connectivity?
Not necessarily
I would say
connectivity,
no.
maybe.
But the answer is no. You're exactly right. And that's pretty advantageous, wouldn't you agree?
Yeah, that makes sense. Like if they had all that same stuff, that it just wouldn't be super useful, right? Like
that too, but it also, in a way, if you could think back to say like when we were doing convolutional neural networks, right? We had to worry about all this stuff like, with padding and, rotational invariance and all this stuff. In a way, by viewing it through the lens of graph theory, it kind of gives us a way of abstracting all that away, right?
oh, interesting. I'll need to think about that more, but that's cool.
But Jen, does the idea kind of make sense?
Yeah, I think so.
And same with, like sequential data, like we saw with RNNs too. We had the issue with alignment, which we kind of had to hand engineer. But now in the context of graphs, since we have a network that can, perform the same task on different topologies of graphs, in a way that those problems are kind of scraped away for us. So, anyway, something to think about. Please continue, Dennis.
Okay.
I'll try to stop interrupting you.
No, it's fine as long as it makes things clearer. So yeah. So we shall go ahead and train a graph neural network. So here the training follows the following procedure. Training a GNN for graph classification usually follows a simple recipe. So here we embed each node by performing multiple rounds of message passing. So that's what we did for the node classification. Then aggregate node embeddings into a unified graph embedding using the readout layer, then train a final classifier on the graph embedding. So here we sort of do what we did for node classification, but then for the entire, we need to aggregate all the information from the entire graph into using this readout layer so that we can perform classification for the entire graph instead of each individual node. That's the main difference between this and the node classification task. So here they say that PyTorch geometry provides this functionality via torch geometry global mean pooling, which takes in the node embeddings of all nodes in the mini batch and the assignment vector batch to compute a graph embedding of size batch size by hidden channels for each graph in the batch. So the final architecture for applying GNNs to the task of graph classification then looks as follows and allows for complete end-to-end training. So here we shall create our layers, our conv layers. So like we did earlier, we have dataset, number of node features by hidden channels. So we have, in this scenario, we have 3. Then in the end, we have our linear layer, which will be used for classifying the graphs into different categories. So the linear layer output here is the number of classes that we have, which for this data set is 2. So we have forward. So we pass it through the 3 conv layers, followed by the mean pooling, the global mean pool, which aggregates our information, like what looked at here, which is the readout layer. So it aggregates the information from all the nodes within the graph. Then we apply dropout, and then pass to the linear layer, which then proceeds to perform classification. So in terms of training procedure, it doesn't differ from what we had for node classification. And as well as for the test, there's a node difference. And we're going to run this for 171 epochs. And once we do that, we shall see that finally our accuracy gets to about 76.33. But you realize that the accuracy within this method keeps fluctuating, which we can explain by the small data set that we have here. So as one can see, our model reaches 76% test accuracy. So the reason for fluctuations in accuracy can be explained by the rather small data set, only 38 test graphs, and usually disappear once GNNs are applied to the larger data sets. So I think that's it. Do we have any questions?
If you guys are interested in this, we encourage you to go through the PyTorch geometric documentation because it's really a great resource overall for dealing with graph neural networks, not just for writing the code, but also for learning about them and ongoing research with them.
Awesome. Yeah, this stuff seems really cool.
Yeah, there's a lot of opportunity with these things. They are pretty interesting. Okay, guys.
And also, like, I understand the code structured in a way that we get the output, but I don't exactly understand what's happening behind it, like the conversation stuff and all. Is there like a video or something that I can go through to
let me drop these 2 links in. These helped me out a lot when I was first trying to learn about them.
Yeah.
Probably the second one will be a little more direct to answer your question, but I think those should help. Yes, but the the notion of the convolution is, in a way, it's kind of like a generalization of what we saw with CNNs operating on images, right?
Right.
It's that's the easiest way I can think of how to describe it. It's just the term convolution. It's just being used in a way to say that we are performing the message passing paradigm on our graph, and its associated information is being updated in some way
Right.
at a single stage. Each convolution corresponds to a single layer, and you pass your graph through a stage of layers, and that corresponds to your graph neural network. Just as you would pass an image through a set of convolutional layers in a CNN, and that would correspond to your convolutional neural network.
Yeah, but here in CNN we have kernels to learn the weight parameters, and here I was just like skeptical about how the edges connection is considered while performing the operation as such.
Well, you pass the edge to the message function, right?
Yep. Oh, okay. So that transforms it. Okay. That makes sense.
Yes, correct. Yep. If you're doing a task that involves it, otherwise it just doesn't get used. But canonically, you pass the edge information to the message function. Yes.
That makes sense.
Okay. Any other questions, guys?
And the graph structure is represented with the adjacency matrix, right?
That's correct. Yep.
Right. So wouldn't the data be sparse?
Yes, it would for computational efficiency. Theoretically, though, you could use any number of representations. But yes, I believe PyTorch Geometric uses the sparse representation.
Right. I see.
Yep. Any other questions, guys?
No.
Nope.
All right.
All good.
Perfect. Okay, guys, with that, I think we're ready to disperse. Thank you all for your time.
Thank you, guys.
Thank you.
Good luck with finals.
Yep.
Bye,
Thank you.
guys.